Alright, this is the introduction to spectrophotometry, the absorbance spectrum of cobalt-2 chloride. I'm Nikki.
And I'm Andy.
And this is our presentation. An outline of what we will be discussing in this presentation includes the introduction, which is our purpose of the whole experiment and background information, the experimental, which is how we formed the experiment, and our results, all calculations, graphs provided from our data that we collected, and our discussion and conclusions, given questions from our lab manual. These are our answers and how our data supported them, and our references use our lab book and our chemistry book.
The introduction, or the purpose of our experiment. The purpose of the experiment was to use a spectrophotometer to find the lambda max of cobalt-2 chloride, then to generate a standard curve, and to find the concentration of two unknown substances using this standard curve.
A spectrophotometer is used to measure the absorbance and percent transmittance of a solution. The absorption of an ultraviolet light results in the excitement of an electron gaining energy by absorbing a photon. The higher the concentration of substance, the less light that can pass through, and the higher the absorption. And the absorbance of a sample is measured at a particular wavelength.
Okay, the percent transmittance is a percentage of initial light that can pass through a substance, and the absorbance is directly proportional to the concentration, represented as C, path length, represented as L, and molar absorptivity, epsilon.
The lambda max is determined by using the spectrophotometer and measuring absorbance and percent transmittance at different wavelengths. Within the experiment, the known concentrations of two cobalt chloride solutions were given to us, and we had to determine mathematically using Beer's law to determine their concentrations at the end.
Okay, for the experimental, we had a cuvette and we filled it 2/3 way with DI water. We zeroed the machine using the zero button, and then we put in the cuvette filled with the DI water into the compartment, the sample compartment, and then we 100%ed the machine using the 100% button at a 400 nanometer wavelength. At 25 nanometer increments, we found percent transmittance and absorbance. And we used the mode button to switch back from transmittance and absorbance. And then lambda max was determined by comparing the absorbance and values of the different wavelengths.
The second part of the experiment, the spectrophotometer was used to, it was set at 500 nanometer wavelength, which was lambda max, and we created 8 dilutions of cobalt chloride and water, all equaling 5 milliliters. Different concentrations were also determined in the pre-lab. So we set the machine to 500 nanometers, measured each of the 8 dilution cuvettes, and a standard curve was created from the data that we recorded of each percent transmittance and absorbance recorded. And we used Excel to generate the best fit line for the cobalt chloride.
Okay, so here are the results from the construction of the absorbance spectrum. The table shows the results of the testing of the 0.15 molar per liter of cobalt-2 chloride from the 400 to 600 nanometer wavelengths. As you can see, the different transmittance and absorbances, and we determined the lambda max to be at the 500 nanometer wavelength. As you can see, it has the highest absorbance and the lowest percent transmittance.
This is a sample calculation for absorbance using the 400 nanometer wavelength. You use absorbance is equal to 2 minus the log of a certain percent transmittance, and at 400 nanometer wavelength, our percent transmittance was 83.8. And using the calculation shown, we calculated that the absorbance was 0.076 without any units.
Okay, here's the results of the absorbance spectrum. As you can see, these are different wavelengths ranging from 400 to 600 nanometers. And as you can see, our lambda max was determined to be the 500 nanometer wavelength. And as you can see, it peaks at 500 and then goes back down, which supports our lambda max of 500 nanometers.
This is our table 2, which was displaying our different concentrations determined in the pre-lab, and our 8 dilutions, the volume of how much cobalt chloride was used, and how much water was used in each test tube to create the dilutions. And then from each test tube, we use the spectrophotometer to determine percent transmittance, which is shown, and the absorbance. We can see the direct relationship between concentration and absorbance, seeing that as absorbance increases, concentration also increases, but as percent transmittance increases, absorbance decreases.
Okay, here are results for the example of molarity concentration. So the molarity of the concentration times the volume of the concentration equals the molarity of the dilution times the volume of the dilution. So we wanted to solve for the molarity of the dilution, so we rearranged the equation, and we found that the molarity of the dilution was 0.0600 moles over liters.
This is a sample epsilon calculation for test tube number 3 again. We use Beer's law, which is absorbance equals epsilon times concentration times the path length, which was a constant of 1.00 centimeters. Using the epsilon, which is our absorbance at test tube number 3 was 0.288, and using all of our calculations, we found that epsilon equals 4.80 over liters over moles times centimeters.
Okay, here's our standard curve. As you can see, we have our best fit line and the different concentrations. Down here, the different concentrations and the absorbance that fit on the concentration. And they were plotted using 500 nanometer wavelength. And this helped us to find our unknown concentrations.
This is our table for our 2 unknown solutions. Andy was given number 43 and I was given number 44. Using the spectrophotometer, we put our 2 unknown solutions in the spectrophotometer and recorded their percent transmittance and absorbance. For Andy's, it was 35.2% transmittance and 0.454 absorbance. For mine, it was 30.6% transmittance and 0.514 absorbance.
So here's our calculations of the unknown, which is my unknown. As I said, we used the best fit line to find the equation, and mine came out to be 0.0933 moles over liters.
For my unknown, which is number 44, we used the best fit line, which we had on the graph before. We plugged it into Beer's law, and using the absorbance of mine, which was 0.514, and using epsilon path length, which was constant 1 centimeter, and the concentration, and the y-intercept, which was always 0.0315, we calculated my molarity to be 0.107 mole per liter.
Okay, so our first discussion question asked for the relationship between absorbance and percent transmittance. And using our table 1, you can see as transmittance is high, the absorbance is low, so they are inversely proportional to each other. As you can see, for our lambda max of 500, it had the highest absorbance and the lowest transmittance.
For question number 2, we had to support our lambda max decision, and our data supported our lambda max at 500 nanometers as shown in the highlighted row. The percent transmittance was the lowest at that point, and the absorbance was also the highest out of all of our test tubes. So by determining the highest absorbance, our lambda max was set at 500 nanometers.
Okay, this is the relationship between the concentration and absorbance. We found that they were directly proportional to one another, and this supported Beer's law, and Beer's law says the higher the concentration, the less light that can pass through the sample. And our own unknown calculation concentrations were calculated to be 0.0993 moles per liter and 0.107 moles per liter.
Our final conclusions for number 4, a total wrap-up of our experiment. We determined absorbance and percent transmittance were inversely proportional, so as absorbance increased, percent transmittance decreased. We determined that there's a direct relationship between concentration and absorbance, meaning as absorbance increases, concentration increases, and this gave rise to our best fit line on the graph. Unknown concentrations were calculated for our 2, determining, using the best fit line, we determined our 2 unknown concentrations, which were 0.0933 for number 43 and number 44 was 0.107 moles per liter.
And these are references. Thank you.